all of the bits. So welcome to the assembly. We're going to do something that's called a universal joint. It's a very common part. It's something that we use to transfer mechanical force around corners, especially in terms of torsion for lots of different kinds of assemblies they're used in the steering shafts of basically every single one of your cars. It's how you connect something with a hard, fast linkage to something somewhere else that has to go through a bunch of unusual angles, but still be very rigid for the purposes of driver feedback and things like that. Some of the time, these are starting to become less mechanical linkages, and they're starting to become drive-by-wire or servo-driven, where you don't have a mechanical linkage anymore, but those are still a little bit uncommon for now. So this is something that's been used for a long time, but this is going to be multiple different pieces. So we need to take each of these drawings and turn them into the actual parts. And what I'm curious to see is if when you guys open them, what I'm betting is going to happen is, because I didn't send the parts as well, they're going to look for a reference to the actual part, and then probably what you're going to get is errors. So I'll have to go in and see if I can resave these as PDFs. And that way you guys can actually access them, and that might be a little bit easier, because the default is you have to save it as a drawing first, then you can save it as a PDF because reasons. So I'll pause this for a second and do that real quick for each of them so that you guys actually have the PDFs, and then I'll update in the class what that needs for that one. All right, so starting from the PDF, we can see a couple of our key dimensions. Have to move our toolbar a little bit out of the way to make sense of it. But what this is going to do is give us our starting point, which should be something about here roughly. I'm going to narrow this just a bit to make life a little bit easier, be able to see a little bit more of what we're working with. And this way I can switch back and forth between some of the different drawings a little bit more easily for the purpose of the recording. So you want to start with the base. It's kind of an important piece of it, and you'll see why shortly. This is meant as a mechanism to retain the U-joint. So this bracket is pretty straightforward in terms of how it gets created. Number of different ways that you can do it. You can do just a simple line drawing. We haven't done a lot of those, so we'll do this from the front plane, and I'll make adjustments to our view. So we'll start at the base corner. Want something that is parallel, and we'll do some rounding later. So we get a rough geometry set up. As a starting point, come in and use smart dimensions. Uh, 82.5 millimeters or 82.55 millimeters is the interior distance plus the exterior thickness. So 6.35 plus 6.35 for the thickness on top as well. This is why when you get to learn GD and T later from folks who could tell you what that stands for, I say in jest. You have a lot of options for how that can be done. You have a lot of options for how these things can be treated. But at the end of the day, what you want to make sure of is you're accounting for all of the tolerances for all of the parts that you're paying attention to. So we need to likewise make sure the distance here is 6.35, because otherwise that'll create issues with the part on the hole. So this length here to here, 42.77. That leaves this top piece, which we need information here about. So sometimes it can be a little bit unclear from this what is and what is not part of, for something like a top view, what is and what is not part of it. The key sections are, you know, that there's some sort of a rounded edge. So it has to either reference this front edge or this back edge. And in this case, this drawing is referencing that front edge. So from the front edge to, in the example here, the base of this circle, not center to center distance, but the actual base of the circle, that's 44.45. And so a lot of times they'll try and trip you up with something like this, where you add a center to center distance and a diameter, and then you know something about the total distance here. In this case, they've given the total distance of 57.15, but that won't necessarily always be the case. Occasionally, you'll have to find it yourself. So here, distance from edge to, very importantly, the front edge is 57.15. And that means we can, from the rest of this, get some of the information about how far out this actually goes, because you see what the relative ratios are. And so you know that very likely this leg has to be about the same overall distance as this front leg, or very proportional to, because we're still way outside of the desired ratio here. So 57.15, and then what we need is this interior dimension. And because this is approximately symmetrical, you could do some additional measurements. This might be one of the dimensions that they leave off on a part, and so you have to scale it. And so let's take a look at what 42.77 looks like. So that looks like that comes down right about the center line, or just above the center line. If we did the same thing, that would come down just above the center line. So that dimension is probably about correct. The reason that it doesn't automatically display is when you are using these, when you're using these sections, and you're using some of the autofill dimensions from the part, if you have radii and things, it will default to taking some interior measurements and not giving you sort of all of the detail there. So those are important ones to note. And so especially in a drawing like this, if you're not given, for instance, the radius, what you have to do is you have to make your part roughly the same size as your drawing. And then there are ways to actually overlay the drawing and things in the background and do tracing and some other things. It's not strictly necessary for this, but you know, based on the thickness being 6.35, it's not going to be a radius of 20 or something like that. So it may be a radius of 10. You can look at a couple other aspect ratios. A radius of 8 looks a little bit smaller, maybe, than what this is. So it might actually be a radius of 10. But if you draw that circle what it looks like is even if that's a 6.35 thickness, you're maintaining that thickness through here. So it's probably closer to about a 9 because this doesn't come in nearly as far. So you can try it and see, but what you're going to notice is this is maybe about 1 millimeter to the inside. So this radius actually has to be a little bit smaller, like a 9, and that's going to match up pretty nicely. So the same thing is going to happen for this one, as well as for this one. Those are all going to be the same radii, generally speaking. The radius doesn't actually, that's actually a great question. The radius, if you did a radius, let's look at that real quick. If you did this radius as 6.35, what you have is you would have in the actual part itself, what you would do is, let me do a markup on this. What you would actually have is straight vertical and straight horizontal. If you had a 6.35 radius, what that would mean is your curvature would start and end at the parallels to your thicknesses instead, which is not what they're doing here, but they're about this radius here. They actually do line up. So if we take away these two, so your view isn't obstructed. The other thing to note is if you bring these out to the part itself, this is before the radius. So you know that's got to be small. That radius, those radii end at the same point. So those radii are meant to be part of a circle, basically. And that circle, you'll be able to kind of see where they're pointing to, because that base goes here. So that arch and this arch are separated by exactly the same thickness. So if you have a radius here of 9, for instance, I think you're pretty close. 9 minus is going to be the next radius. So this one is going to be 9, is going to be 9 minus 6.35, so that you can take into consideration those two. So then what you have is the two lining up and looking identically placed, right, with about the same thickness. Those two would line up. So this is how you can tell and do kind of some quick estimation if somebody gives you a drawing and they haven't necessarily given you all the dimensions, like say, for instance, in the assignment where we're not going to give you all of the dimensions because we're mean that way. What that's going to do is that's going to give us kind of the operating parameters. So somewhere around 9, it might have been 9.35. It might have been, it had to be more than 8 based on this, but this gives you the same, what I keep referring to as an aspect ratio. So if we look at this side by side and we bring this in, those look virtually identical, and that's why. So this one, same thing. It's also going to have a radius of 2.65. And then this interior has a very small bend. So it's also going to have the same radius, but it's going to be very, very small. So now we have all of our radii accounted for. We have our dimensions, and we figured out the pieces of information that we're missing based on the aspect ratios. how big something is relative to something else, right? So now we need our top piece and we need to do our extrusion. So we're going to jump out of the sketch fillet and we're going to extrude first. And our extrusion width is 38.1. So 38.1. And we need I'm going to square this up for a top view. So what we're doing is we're now recreating this. Note that the bold lines are the things that are closest to you. The faded gray lines are a little bit farther away. So those are important things to incorporate. So this now, we need one more sketch. We need it to be on this top plane of this part. And we need to jump from one edge to another, but we need a center line from which to do it. And there's a reason that we want a center line, just because this gives us a really solid anchor point. We can use another center line somewhere. I don't want to associate it with any other points, center lines, corners, fold lines, or any of those things. I want to be able to control the dimensions so that I can get this 19.05 spacing that I'm looking for. No, that is not the smart dimension I need. Every once in a while, Solidworks likes to help. Or if you buy a mouse on Amazon, sort by cheapest, sometimes you get a double click when you don't need it. All right. So 19.05. And then we need our through hole that's going to be at that intersection with a diameter 12.7. So now we can do our extrude cut from the sketch plane is fine. But what you want to do is you want to change it to up to next so that you're not doing a through all and messing up the mass, center of mass of the part, etc. For this purpose, we're not necessarily going to be changing the material for this one. What we're doing is just creating each of our individual parts so that we can make an assembly. So this one's done. We save as, and then we say, let's do, I'll bring it to this semester's folder. And this is the, I'm going to create a new folder because this is going to contain all of the parts. This will make it easier to find stuff later. If it's not just a random assemblage, it's actual group of part files all together. So this is the bracket. So this is the first part. We're going to create a couple more pieces. The fillets, this is part of the reason why I wanted to make sure all of the details are in the recording, because the fillets themselves, what I did were sketch fillets. You could do the fillets after the fact as well, but it's going to be easiest to visualize here. What we were doing in terms of reference was we were kind of taking a careful look at the part and we were inspecting some different radii for things. We found that 10 was maybe a bit aggressive. 10 is a little bit too far toward the top of the part. Based on the interior thickness, we can estimate what that thickness needs to be pretty closely. And that's why what we needed to do was zoom in to see where the lines actually start curving. And so from here, it's about not quite a third of the thickness, a little bit less of the thickness, to be able to figure out what these radii were. And the difference is we need to be able to measure. We need to be able to measure. So from here, I'll do it in red as to make it very clearly visible. So in red, we have our semicircle here. So this is an arch. We know the distance from here to here. I'm going to do this in green. We know the distance from here to here is 6.35. We know that's uniform throughout the whole part. And we know that there would be, so something that we basically have to figure out is from, let's try that again. That was too high. I'll start it from here so that it's at the right height. So from here to here, we can see that that angle is not actually 45 degrees, but we know roughly from here how much this distance is. We can do some more measuring tricks and things if we need to for a particular part to get the mass closer and closer. But basically what you're doing is we know this total radius. So I'll do that in purple just because. Let's see if I can get it to allow me. So the total radius, I guess I can kind of do it parallel. The total radius is this minus, there's a total distance, and it's going to be this distance and this distance are going to be almost double of each other, but that radius is going to follow a circle so that there is always a difference between the two thicknesses of that 6.35. So it's a little hard to show in the actual with the actual lines themselves, but that'll give you at least an idea of what we're aiming for. And then they're just done as a sketch fillet, and I entered this as the formula for subtracting from the 9 millimeters that lined up pretty nicely with the drawings and got us the correct aspect ratio. We went from there to the formula where we subtracted the 6.35 millimeter thickness. So now we have our part, and that's saved. So now we need another part, and we'll jump to the second drawing. So we need the crank arm. This one is going to be pretty straightforward because really most of what you need to know is all right here. So for this one, I'm going to do another quick sketch. I'm going to do top plane. And this one is a rectangle with a couple fancy cutouts. So this is 75. This is 19.05. Okay, so our aspect ratio is about the same. We're going to need a center line to reference our cuts. And we're going to need a couple more. So you want to make them at least parallel, but the center lines are really going to help you for later to get everything lined up. So 9.53 from this edge. And 9.53, so it's a square pitch, which is nice. Pitch just means center to center spacing of the holes. So it falls under the category of the more you know. So we zoom in and we have one. We zoom in, we have another. And then from this, we have a line that we generate. We're not going to associate it with any other points or references except being horizontal. And we're going to set that distance, the distance from the line to the center, as our 4.89. So then we come in, trim out the unnecessary sections, and we're left with our D-shaped crank hole. And this is a radius of 6.35. All right. This one, it'll only give you radius because it's an arc at this point. So it's not a full circle. You can't specify a diameter once it's already been cut. Just one of those things to note. So if you're trying to figure out how to do something, remember you can always divide by 2 or multiply by 2 to get back to the number you needed. So we extrude this by 6.35 millimeters, and the crank is done. So now, this is the crank arm. Okay. So this one can go away. This one can go away. No. Then we also need the crank knob. I'll go ahead and open the rest of these. Because then we get to basically do an intensive lesson in how the assembly mates work for multi-component assembly like this. And that's why I chose this example for today. So there's a lot more detail to cover. So this one, it's a little less obvious how to proceed. And it tells you some things, but you have to figure out what things it's telling you. So I left these intentionally a little bit unclear, so that you guys had to kind of think your way through what this looked like. A lot of times we're going to use a given radius or range of radii for a part to do something. So there's a couple of ways that you can approach this. The first is you can do a bunch of extrudes and extrude cuts, but can you guys think of an easier way to do it? What's this an ideal candidate for? Before you guys think in terms of I'll just extrude a bunch of discs and then do some filleting at the end. What's a better mechanism to use? Yeah, exactly. A revolve extrude, because you can get most of what you need in terms of the geometry and it's symmetrical. So the reason you know it's symmetrical is comparing the side view and the front view, and both are identical. So this is a symmetrical part, which makes your life a lot easier. So you start with a center line along a front plane. All right. Recenter your view so that you've got an idea what you're working with, and then draw half of the part. So you know that there is, and this one can be done freehand. We'll go ahead and do that so that you can see what it would look like. Here and here and here and here. Okay, so this is your freehand line drawing of this. And I'll show, just for the sake of, I guess, completeness, what the goal is there. I'm focusing in on this half where I've got this line. I have this box coming back to this line, coming back down, and coming back down again. And this is the half that I'm drawing so that we can bring in the radii later, because all I need is a few of the key dimensions. So I'll go back to the pan so that you can see what's going on there. That means that I know what the height difference is here to here. So here to here is 15.88. And I know here to here is 6.35. So there's a bunch of these dimensions that you'll recognize from some of these other parts, in terms of some radii and things. That's to make the actual end part a little bit more uniform. So there's a bunch of reasoning behind that, actually, but there's good reason for it. Now, they don't give you the overall diameter of this, because in the part drawing, what they're going to do is they're going to give you a couple pieces of the information, but not all of it. So one thing we know, for instance, is we know this radius is a sweep of a full 90 degrees. So that gives us some very important information. So this here, we can start by either, there's a couple different options, but the easiest way is going to be not to go ahead and move it. But what we can do is we can cheat, essentially. And so even without the information here, what we can do is say, okay, I've got enough information here to know how to be able to work on this. So what I can do is I will keep the endpoints of the arc. And what we can do is we can set this edge, instead of drawing out to here, what they've given us, we can actually draw it out to here. So we know this radius comes all the way up to 90 degrees. So we know what this distance is as a result. And then we can just use that edge and draw this portion of the box instead. So we're drawing this portion of the box, and we'll add an arch at the end with a known radius. And that will get us pretty close, because we know something about this distance based on this. Center to center distance of that outer ring, if we were to, let's see if I can get it to reposition here, because it'll have to be double that. So right about this size. So if we center that, it's maybe a little large, but if we center that, what we'll find is, there we go. That's the distance or the radius for that lower circle right here. So it's the same as the radius right here, 4.76. 4.76. So they're using some common dimensions. And if we know that radius, then we default know what the rest of it is, based on the other things that we've learned. So we're going to set this first. We're going to set the distance between the center line and this point as 4.76. Then we're going to set this arch because we know what, especially because we know, having just built the part, what dimension this pin is going to need to be. So 6.35, you should recognize from the last part. Somebody go back and look at that part drawing and see what the diameter was of that pinhole. And I think you'll find the other answer that we're looking for there. So this point is going to have a sketch fillet. It can't be 10 millimeters, but we know it needs to be 6.35. I'm going to clear selections and use it here. There we go. So we know that goes through a full 90-degree sweep. 6.35. We know this is spaced correctly. And we know this arch now. We can make the distance between this and this to be 0. So what that does is that effectively eliminates that center section. So now we have our 6.35. And we know, based on that crank arm drawing, what the diameter needs to be, because the diameter itself is this 4.76 right here. So we know this has to be 4.76 divided by 2, and that locks in this dimension. So now we have this radius. Now we have the upper arch that's going to give us what we're looking for in terms of the radius. And what we're going to do is we're going to do both ends. So 1, 2, and then 3 happens to give us our radius of 4.67, because this arc has to be 90 degrees based on the relations and the constraints. So now we eliminate it, and now we have our revolve. We're going to go ahead and connect this so that we have an enclosed area. But what that does is that gives us enough now that we can do the revolve and give us our part. So we have our knob. We'll change the material on this one just to distinguish it. We're primarily concerned about the appearance. So maybe we'll do something like a beryllium copper, give it kind of a nice red color. I've seen that referenced in a couple of those drawings. Yes, we need to save that. So So we've got a few more pieces. This one we don't need open. This one we don't need open. This one I'm going to leave open in case we have to make a minor adjustment because of constraints. I don't think we will. But let's go back to the pin. We'll need 2 of those. We only need to make 1. This one's going to be super duper confusing. All right. So 9.4 over 2. Extrude to 38.1. And I'm going to make these in something that we can see. Again, I'm going to change the materials just because something like something dark like ductile iron, so they'll be clear where those parts start and end. I'm going to save that as the pin. All right, so that we won't have to change dimensions for. We're now going to go to the spindle. All right. 19.05 square. So we need 1 more new part. None of these parts are particularly challenging. That's part of the reason why I like this as an example. So we'll do right plane for this. Number of ways that you could do this. It's also important to understand that this has through holes, so it's not a shelled part exactly, but it does have through holes. So there's one sort of trick about the way that this works, and you'll see that when we go to put together the assembly, because the front view and the side view have about the same properties. So the side view and the front view. So this has a through hole going along on 2 axes, but not through the top and the bottom. So that's going to create some interesting intersections in the part. So we'll look at how to at least know that those are there as well. So 1905 on a side. And you can reference the 2. So we can do that just by touching either of them and referencing. Kind of saves you a couple steps if you are trying to work efficiently. It can make life a little bit easier. So 19.05 on a side. So a couple ways you can do this, one of which is to cheat and set the distance to be 0. Then set your diameter to be 9.553. All right. What you can do is then extrude this, and we're going to create the cut on the other side as well. So this is actually a cube. So we've got the top view looks the same, but now we need the front view to look the same. So easiest thing to do is another sketch on the front, reposition to make life a little easier. So referencing both of those midlines without clicking, you just sort of drag them across. 9.53. And we do an extrude cut all the way through. So now we have our spindle. And this technically will create interference with pins. It's normally done just a little differently than that. Normally the pins are offset, but because of the clearances in this one, you have to use this square part, so it creates a little bit of a strangeness to the part. To have a spindle, it has to have multiple pins, but understand that this isn't a sort of a real mechanical design that you're putting into production. This is just a reference to understand the assemblies. Spindle. So then we have the two yokes, and then we're done. So this front and side view are distinct to give us an idea of what's going on. Make sure I can see well enough. All right. So spindle. Now the next question is, before I go ahead and start this, what direction do you guys think I should start this from? What do you guys think? Based on the images. So I'll add a quick label to make life easier for you guys. So we'll call this side view, and we'll call this front view. So side view over here, front view on the right. Which side would it be easier to get the most of the geometry from a single block? What would be the recommended series of operations if you guys had to create this part on an exam? So I see one suggestion. What do we think? What angle, or do you approach it from the top plane? Because there's a way that's easy that gives you everything you're looking for in terms of the geometry and the through holes. And then there's a hard way. Because if you take it from one of the sides, then you have to turn it into a cylinder, having started as a rectangle, right? So what I'm trying to get you guys to think about is, does that give you enough of the geometry, or do you start with the cylinder from the top and do an extrude? That's one operation, one sketch. Then you'd have to do the side cut. That's another operation in another sketch. Then you would have to do the front cut as well. So that's another operation in another sketch. Is there a way to build this part without 3 operations, or is 3 the minimum? Tell me in the comments what you think. What's the minimum number of operations? Is it 2? Is it 3? Is it actually really 4? I'm curious to see what your thoughts are. How many of you are just holding out for me to pick a front plane or a top plane or a right plane so you know what the answer is? That's probably quite a few of you. So the answer is, in short, there really isn't a wrong approach to this one. Really, your operation has to be 3 steps. It can't be less than 3. It's not reasonable. So we're going to start with the couple that are debatably the most important. And what that is you can create the cylinder and do an extrusion there. Then you can create the geometry that is the most symmetrical throughout the entire part is in fact the cylindrical part of it. So in this case, I'm actually going to recommend, because of the sake of speed, you would start with a top view to make something like this sort of a geometry. So you have an inner circle, an outer circle. Because as nice as it would be to do this and do a side cut, you're going to have to do, in this case, all 3 of the sketches on 3 different planes, no matter what you do. So 38.1, so everything has a consistent width. 9.53, and we extrude 47.63 from our drawing. So now this is the new top. So we're going to do a sketch. We're going to do this referencing the front plane. So just for the sake of not being confusing, I'll actually do a right plane sketch. So click or right click the right plane, add a sketch. I'm going to reorient our view just to make sure that I'm keeping everything nice and square. So there's a couple things that we need to know, one of which is we have a reference center line going through this, and we have a height. We're going to need a center line through the center as well. These reference lines, again, are going to be things that are immensely helpful to us, but we have to be kind of careful about how they're arranged. Because one of the things that we don't see, for instance, is we don't see much about the actual height. So we know this height to that top edge is 29.21. Okay. So what this is going to do is we're going to create this sketch, and then we're going to go back and recreate sketch 2 on the front plane. It'll probably be named sketch 4 because reasons, but we're going to go ahead and get our circle in place. So down here, We have a radius of 9.53. We have an overall distance here, 19.5. So we know a couple things. We can reference the rectangle to be 19.05, or we can separate a couple lines by 1905. But the rectangle is going to give us some distinct advantages. And in order to keep stuff centered, I'm going to reference the center line here. So this needs to be 19.05. Now we know a couple of other things. We know the dimension of this, or the diameter, needs to be 9.53. And we know there needs to be this circle. Again, when we take a look, even though this information isn't strictly specified, we know that this circle is parallel by the thickness here. So how do we know the radius of that circle? Somebody who's really good at math, tell me what the radius of that arch is. I'm going to set the smart dimension here to set our height. What do you guys think the radius is of that lower arch, since they didn't give us the dimension, except they really did? So if we did a center point arc, I'll do it here somewhere else just to give us a reference point. So 180 degrees. Even if we didn't see it, how would we figure out where that center point is? We would know the radius of our arch because it would be 19.05 divided by 2, which gives us 9.53. So now we know that height difference needs to be 0. And then we can come in and trim away the stuff that we don't need in here. Now, in order to do an extrude cut in the way that you've seen set up here, there's another thing that we have to do. So I'm going to eliminate these and our cross braces because we don't need those now. Sometimes it can be harmful to eliminate that many references. In this case, we're going to be just fine because we need to do some filleting. Now, they didn't give us a height here, but we know something about the radius here, 9.53. So if we were to take an arc and bring it forward, we know the height. We know the height here is 29.15 to the top of this rectangle. So 25 or 21.9 or 29.15 is what we're going to use as the reference. So this height is going to be our 29.15. And we know that this arch is going to come all the way up to this point. So that arch is going to be 90 degrees. So we know something about our arch here needing to be 90 degrees and a radius of 9.53. And it'll reach. So now we come in and trim, not smart dimension. So now we do the same thing on this side, or if we were smart, remember we can do that half thing, and we want to mirror this about this, then come in and trim our entities. So always be thinking about what tools you can use to take advantage of this. Now, another thing that's actually pretty important, this boundary is going to need to cut. So think about this in terms of a cookie cutter. A couple things are going to be needed. We've got to connect the top here. So we've got to make this almost the inverse of a cookie cutter, and it'll probably make some sense why later. So what we're going to do is we're going to add a rectangle on the outside so that we have an enclosed region, and you'll see what region I'm going to pick to do the actual extrude cut. This is a cookie cutter method, and we need the interior region there, and we need it to cut through all, but we need it to cut through all both directions. So what that does is this effectively creates a cookie cutter effect that stamps all of the material or cuts away all of the material in one go, because it's very hard to define. Sometimes you can get conflicts with interior edges and things. If you haven't done your dimensioning or mirroring very properly, this will save you quite a bit of headache and or time just to throw an exterior rectangle on. Now we need to do this one, which is going to be our front plane sketch. And this one's going to be the quickest of all, because we know what that needs to be. We have a center line. We have a center rectangle. We have our smart dimensions of 29.15. 29.15, and then our width is going to be 20.32. And we want to set this distance to be 0. And what this is going to do is this is going to create the cut. The reason I did this in order of operations is simple. I'll do it with the other order of operations to show you what I mean by that. But here we're just going to take that interior region and we're going to do an extrude cut of this whole region, and it needs to be through all both. There we go. Even though through all both was selected, that creates an issue. So note this, this particular feature, this notch, that notch would not be present if we had done it the other way, in the same way, because we would have ended up with a different reference point, and these two pieces would have been joined on the side. So doing it specifically for this order of operations is what gives us our particular geometry. So now, here's another interesting thing. If we take all of this information and we say, okay, that's the female part. So we save it. So this is now we have one more part to create. And that is the male yoke. Okay. So this is the counterpart. Now, what do we notice about this yoke? Anyone notice anything interesting? What do we notice about that yoke? Are there some similarities in dimensions? Yeah, exactly. The other yoke basically is the same geometry. Looks like it's the same overall heights based on this. 47.63. But then it just has a pin on the top. So what we can do is we can take advantage of this part, save this part with a second name. So we can say yoke male, save it. What we can do is we can do another boss extrude. We're going to pick from this original sketch. We're just going to pick up to next. Actually, we're going to pick from surface, which is this surface, opposite direction. And we're going to go, it's not going to allow up to next. So we're going to do up to another surface, which is going to be this face. And we're going to select for the contours, not the whole of sketch one, but just this interior piece. So when we do that, we fill in the top of the yoke. Then we can create the entire rest of this geometry all from right here. So how do we do that? Well, we pay attention to this part of the geometry, try and make it as big as I can. So we pay attention to this part of the geometry. We know what our extrusion height is going to be, and we can taper it at the end. There's ways to make that easier. There's ways to make that harder. The easiest is going to be to come back in and do an extrude cut for this small section, and we'll show how to do that. So order of operations does matter, just like it does in math. It matters in CAD work. So what we're doing is taking this 12.7 diameter pin. We're going to start it on the top. So we've got 12.7 diameter, 7/2. Then this pin gets extruded. We're going to end up with a taper, and we're going to show you how to do that kind of a taper. There's a couple ways to do it. We're going to do an extrude cut second, and that's going to be this 1.59. So we're going to do just out here horizontally. We're going to set the dimensions between this and this to be actually, we want to delete that one. What we actually want is from this line to the edge. The easiest way to do a calculation for one of these is to take your diameter of 12.7 over 2, and then subtract from that 1.9 or 1.59 to give you your effective distance so that you're referencing the center point rather than the exterior. And then we'll validate that this is indeed 12.7. We'll get to our fully defined sketch, then we'll cut out the pieces we don't need here, and we'll do our extrusion. So our total extrusion here is 19.05. So we're going to extrude this region and this region. So these two, we're going to extrude both blind 19.05. All right, now what we're going to do is a note that we lined this up. I didn't mention it specifically because of having the part oriented and going back and reframing correctly using the geometries. I didn't have to think about, oh man, I got the D cut on the wrong axis or whatever. It was already on the correct axis because I knew what reference I was working from because of the top view, and using the top view as a default, I knew where I was. So defining right side, left plane, right plane, all of those seemingly dumb details do in fact matter, and they matter significantly. So instead of a fillet, we're going to do a chamfer of this edge, not of the face itself, but of this edge. And what it's going to do is it's going to give us, and we're going to do an angle distance combo. What this is going to do is give us our 1.27 that it's looking for, 1.27 millimeter and 60 degrees. But you can see that's not quite, it's 1.27 on this. Yeah, okay, it is 1.27. So specifically the 1.27 distance on this axis and the 30 degree. Yeah, so this is actually the correct chamfer for this. You can flip the direction. So if that happened to be incorrect, you can flip that direction and say, do the opposite. And that would give a 1.27 dimension on top with a 60 degree angle from the other 90 degree reference. But that's not the case for us. This is actually the correct chamfer. Then you do your extrude cut as the last step. You find that sketch for this one. And what we're going to do is we're going to do an offset from the, we're going to do an offset. There's a couple ways to do it, but you can also do it from this surface. So you could say from here and then just go down as a blind, and it would be 12.7. So you could do it this way, and this will give you the correct cut. There's a couple others. This is probably the easiest to conceptualize, probably the quickest in terms of time. So that's probably what I would do. So now we have the male part done. We didn't have to go back and recreate all of that nonsense. So the male part's done. Now we can finally go to put all of this mess together. So how do we do that? Well, we go back to our base and we say from our bracket, make sure that's saved, make an assembly from the part. And now we're going to get into the greater detail. So the bracket, the spindle, these are the things that are currently open. So we're going to do a bracket. we're going to bring in some of the other parts. So we're going to go ahead and bring in a spindle, which we're going to need. We're going to bring in the male yoke. We're also going to bring in the female yoke and the pin and the crank knob and the crank arm. And so we're going to place these, the pin, the other yoke. All right. So we have a bunch of gobbledygook. We're going to need one more pin. So it's easiest just to insert the pin one more time. All right. So we can notice a couple things about how all of this goes together. The first part that I brought in is the bracket. What that means is that is fixed. So remember the float fix trick. You want to make sure you have something that is fixed in a geometry so that you can understand what it is that it's doing. So what we want to do is start adding our I'm going to change all of my display style to be the same. This one right now is viewing as wireframe, but that's not, yeah, we don't want to hide components. We want to unhide. I want to show the components. So what we'll do is we'll start working with, yeah, we actually don't want transparency, but it'll give us a little bit of better visibility as we go to start aligning a couple of these parts. So first thing to focus on that's going to be a little bit easier is going to be putting together at least the parts of the subassembly. So, and there's one more, actually, I think there's one more part. Yeah, the actual crankshaft itself. So not the crank arm. There we go. Yeah, we missed this one. So we need this one more coupling part in order to make this. Now, here again, we can make some use of this part, but that's actually going to be it's actually going to be a little bit harder to do, but not impossible. So let's do that real quick. 6.35, and so we've got a couple changes to our taper. Okay, so I'm going to teach you real quick one more thing about how to repurpose a part, because we are going to need that. When I'm going to go back to this part drawing, you can see there's some similarities between these. The base circle is still 12.7, but we need to change some of the parameters, the taper, the depth of the cut are the main ones. So that's what we're going to do, is we're going to resave this part as crankshaft. We're going to resave this part. That way we're not messing up the part that's already in the assembly. It's really, really important to do that. So we're going to edit this feature. It actually needs to come down now, 6.35 as the thickness. The chamfer, we're going to edit. So it's actually going to be 0.79 and 45 degrees. So slightly different chamfer. All of that stuff messes around with your part mass slightly. So things that you really need to pay attention to. Now, how do we turn this into our base? Well, what we can do is, so long as we've got an overall height that's the same, We can start from this side. So we're going to adjust our view, again, trying to keep things square. We're going to add a sketch, and we're going to reference the right plane. So this sketch, we're going to add a center line. Okay. We're going to start at the top. That's interesting. That is slightly off. I'm going to redo that center line because I think that was not actually completely horizontal or completely vertical. There we go. So yeah, so now it's positioned correctly. All right, so we have a slight difference in what it's treating as the center. So these two, it now has a point of intersection. We are actually going to reference, it'll be easiest to visualize, I guess, with a line. Yeah. So what we're going to have to do is a couple steps, an extrude cut and then an extrude fill in. You could recreate the part from the original geometry. It's going to be a little harder to do, but there's a reason why we're going to want to do this, and so we'll see what that is. This gives you sort of a midline reference for the height, or at least for at least for the height. This gives you kind of a midline reference. So it's not abundantly clear what that's trying to show you, and that's part of the reason why they give you these two radii. But you also know what the overall base is. So you know this height needs to be 40. You know this base needs to be a width of, and you can draw it out. You don't want it associated with any of the other points in there. This needs to be a base of 18.92 divided by 2. And then it goes up. And then we start our arches. So the first actual rectangle height is what this would be referencing. So this height is 15.88. Then that gets blended with this other arched piece. So there's a line that comes down. So you can do a line here. And at this same height, what we can do is we can measure where this changes. So we're going to go to basically parallel with this and come across. What that's going to do is give us the reference points here and here to then, regardless of where those things start, we can start with a radius of 4.76. So this is going to have a radius. You can sort of try and visualize it with a 3-point arc. But that's going to give you symmetry that's not necessarily helpful. So this is where a tangent arc might actually be really helpful. So we're going to go from something like, yes, it needs to be an end point. In order to get a tangent arc, because complicated reasons, you're going to need a point up here to reference. Same thing, you're going to need a point down here. Those points need to remain blue so that they're not fixed to anything else. So we go back to a tangent arc. That is an ending point. This is part of the reason why I don't use a lot of tangent arcs to begin with, because you can use a single point as an endpoint, but in this case, tangent arc is probably not going to be the most effective. So you're going to do it a little bit differently, where you're going to do a sketch fillet. So you want to do this one, sketch fillet. Every once in a while, it'll pick a very wrong parameter for you. And this is going to be 4.76. And you want to fillet these two together. The trick is, even with a base, you can trick it a little bit with a 3-point arc. So you can grab this reference point that we used. I was trying to see if I could make this make a little bit more sense to you guys, but what we're going to do is we're going to generate a point out in space. So we're going to start with not referencing any other point. I'm just going to get another arc to make this make a little bit of sense. Because the radius itself needs to be 4.76. Then we need another arc to come in, and we can, this point can be movable. This point is not anchored, so we can change it so that it's lesser of an arc. And then we can do the same thing for another arc, and a 3-point, yeah, really probably is going to be the best for this. And we set our radius to be 4.76. And what we're trying to do is we're trying to move these points outside of, you want to get out of the smart dimension tool, because otherwise it's going to create some headaches for you that you don't want. Something like this, and then bring this point closer to the two so that you have kind of a free form shape that is connected. The only other reference that you need is right here, a radius of 15.75. So the smart dimension, the point here needs to be, smart dimension would actually allow selection. There we go. This should be 0.75 divided by 2. And so there, is your correct reference for the heights. And now we trim away the stuff that we don't need, including this piece in here. This piece, and this piece. Yes, even though there's some dimensional references. So we'll allow this to be cut off and flat so that we just have that arc segment, and then it's a pretty smooth transition. All right, so now what we can do is take that geometry and use our same cookie cutter concept. Bring that up. So this is now an enclosed region that we can do something called a revolve cut, which you guys have seen before. We want to cut this region all the way around. Hit OK. Actually, we want to extend this down. We actually want to extend this down to the entire thickness for that very reason. Do a revolve cut this region, but we want it around this center line. So now I need a small extrusion so I can add one more line. So I'm going to edit that base sketch and I'm going to readjust the view. That's really important for this specific operation. I need a line that references this plane, goes all the way across and is horizontal. And then trim this piece I don't need, so that then we can do a revolve to get the rest of our base thickness that we need. That needs to be from the same sketch, and it needs to be this small region, 360 degrees. Now I have the full thickness. And on this front, there is a small pinhole for sitting onto the crank. The interior, based on how this is supposed to sit, the interior of this actually should be cut out to match. Technically, we're going to, for the purposes of time, we're going to ignore that small section. Actually, let's see. This is only going to have a depth of, tell you what, we don't have to do that. And here is why. We can go ahead and do that extrude cut in the base because we have this base sketch still, which is this one, sketch 5, I believe. So sketch 5, we can do one more extrude cut because this started from, yeah, the extrude cut we can do for base 5, an extrude cut from sketch 5. And what we're going to do is we're going to do an offset, just a straight offset of this. Actually, you know what? We're going to do it from the face. We're going to do it from this side. We're going to flip direction. That'll make more sense. Blind, and the depth is going to be the same as the height on our, it's going to attach to the top of this. So we know that depth is going to be, that depth for this part is going to be 12.7. So we're going to do a depth of, we're going to do a depth of 12, let's see. We're going to do a depth of 11 because of this 1.27, and you'll see why. So we're going to do 2 steps. We're going to do 11 millimeter. So that's going to be to this base. We're going to pick the selected contours. So we're going to pick these 2. Actually, we're going to pick just this one because of alignment purposes. And we're going to do it from this base. That's going to set up our keyway that will make it easier to do a couple different things, and you'll see why. We're going to do one more cut extrude. We're going to do it from, again, sketch 5. We're going to start it from this face here. We're going to flip direction. We're going to flip the direction, and we're going to give it a taper, and we're going to use this same taper that they gave us of 60 degrees. And we're going to do that for 1.27 millimeters. For this selected contour, we're actually going to do both contours. But yeah, so it should allow it should allow, all right, clear the selections. It should allow the circle region and this tapered region, just like this, which is what we want. The angle is going to be the same there, but it'll be a lot cleaner if we do it this way. So then what we have inside our part is a match to the D shape for our part for the top of the male yoke. Now, the only thing missing in terms of features, we need one more sketch, and we need to reference the front plane. Needs to be a small center line. Needs to be a small hole. Let's go back to this guy, 2.38 millimeters. So even though this started out life as a very different sort of part, 2.38 millimeters, and that's roughly centered on this edge. So what we can do is we can orient our view, then we can do a center line, and we can cheat. This is why we like center lines. Instead of having to guess, do a bunch of math. Nope, not that smart dimension. Try that reference again. There we go. Every once in a while, it does something dumb with a dimension. Don't know why, just know that it is. All right. So now we do our extrude cut of this. But the trick is we need to reverse direction and say through all. All right, so now we have our pin hole for the keyway. What we can do is we can save this. This is now done, and we need that in our assembly. So we switch back to our assembly. So some things, oh, nope. All right. We're going to bring in the, male yoke again, just because reasons. So still there. Now, we've got all of the parts, and at long last, we can put it all together. So this is a much more complex assembly, but you could see something like this where all the parts already exist. So this is kind of the last in-depth part tutorial that we'll be doing for probably the majority of the semester. Now we can start doing our arranging. So this is our fixed part. We want to reference everything else relative to it. So this part is going to be, we're going to start with our mate selection. So that face, I want to make concentric to this cylinder. I want to bring this face coincident, meaning they have a common joining point with this lower face. Okay. Then we can bring our crankshaft up. So this cylinder needs to be concentric to this one. Okay. And we want to, this can still adjust in terms of height, and it can rotate, you can see. So what we want to do is we want to add a parallel constraint. So we want a parallel between this face and this face, so that those two are always going to remain parallel. What that also means right now is we can rotate them together because of that constraint. So it's an important thing to note. So now we need this face concentric with this face. And you'll see what that does is that allows our parts to be matched up into that groove that we cut for this. So now we have those two parts, and now they aren't going to move, but they aren't constrained axially, which we don't want. We don't want them to be constrained axially. So we can leave this at something like a 90 degree, or we can leave it at an off angle. It's going to be easier if we constrain this in a way that it's roughly 90 degrees, just because of some things that'll happen later. So we want to take this pin, and we want to go back to mates. We want to take this pin, clear selections. So pin 1, the actual face, we want to do I want to do this face and this face as concentric. And then we want to set the pins at a coincident point. Actually, this one is a perfect example of when to use one of the advanced mates called width. what that means is I pick the faces of either end, and then I pick the face of this exterior. And what that does is that automatically centers something between the two. That can save you also a lot of time when doing alignments. It's just a whole lot easier. So we'll use the width for this one as well. So we want a concentric first. So concentric between this cylinder and this face. Okay. And then we want to do the same thing where we do a width mate, this face and this face, and you can do it to the interior faces as well. So what that's going to do is center the profile so that you have even spacing, which is actually really helpful. And now this one, we can drop in our second pin. So we want that face concentric to this cylinder. And we'll use the width mate for the edges and then the two faces. And now we can go back and do our concentric with this circle. And what we want to do is make use of our anti-parallel alignment if it makes sense to. In this case, it doesn't necessarily make sense to. It's just going to rotate the part around. So we're going to hit OK. And then one of the things we can do is we can kind of do a manual rotation of this part. So you'll be able to see, and this is where I said we might need to make a slight adjustment to the actual length of this. So we'll see, yeah, it looks like we need just a few more millimeters technically. So we'll get into how to do that and how to update the assembly. So we're going to do the same thing. We're going to do a width mate between this face and this face and these two faces. Okay, so what we can do is set the angle of this a couple different ways. We know what the angle is of our bracket, and so we're going to go back to that drawing briefly. We know what the angle is of our bracket, and it's 40 degrees. So that's one of the things that we have to verify in our drawing, because it may not actually be incorrectly dimensioned. It may be incorrectly angled. So we go back to the bracket drawing. This is why I left it open, because I wanted to leave something to correct, because that seems like it's much more than 40 degrees. So let's take a look. So now what we need is an angle distance, or an angle of, come on, Smart Dimension. You're smarter than that. So that is at 45 degrees, which is wrong. We want it to be at 40 degrees, which is correct. So we exit the sketch, we save the part, and that will update it over here in our assembly, which will ask to rebuild. Yes. So then what we want to do is, if we know this is going to be, if we know this is 40 degrees, we could specify, for instance, an angle between these two parts by finding a flat surface on each of them. And we can specify what's called an angle mate. So again, something that you've seen before, but we want an angle between those two, and we want it to be 40 degree does not quite match up with this. So we need it to be the opposite side of the triangle. So we need it to be In this case, interesting. This one looks like parallel is approximately a 50-degree orientation, which is interesting. So we might still need to adjust the actual length of that part because it might still be just a little bit, might still need to be just a little bit moved, but 50 degrees is pretty close. Let me grab the direct side view here. Before we do this, I'm going to set a parallel and see if that helps. Because one of the things that we haven't set, for instance, is this. So I'll get out of that tool. This part can move in that orientation, as can this one. So we've got multiple constraints. We don't want to set an angle necessarily for the purposes of rotation for this one. But you'll see some of the things that we can do if we do set an angle. The easiest for this particular part is going to be to set up a mate that is parallel to this face. And by constraining it that way, what we're going to do, yeah, it looks like that's just a fractions of a millimeter off. So we might be 1 millimeter off in my estimation there. What we can do is then, as this turns and rotates, it maintains its angle and direction. So now we can put our crank on it. We can say we need this to be concentric to this. We need a parallel between this face and this one. And we want, we can do the top surfaces parallel. Actually, we want the top surfaces to be coincident. And then get our pin concentric with our crank. And add a coincident between this face and this face. Okay, so what that means is then our crank can rotate around and our U-joint assembly, I want to fix that clearance issue just because it is annoying. On that base sketch, edit, we're going to do 43.77. That should be enough to get us our corrected geometry. So I'm going to go back to the assembly. Yeah, reload those parts. All right, so that is roughly interfaced. There's a small collision there, but it's very close in terms of clearance. So it might actually be another 0.5 millimeter. But what this does is allows for the constraints, and you can see where technically the part does bind a little bit against itself, or it would in reality. So it wouldn't actually work at that steep of an angle. So that 40 degrees is really, really sharp for most U-joints, but that's why it has to have the cutaways in the way that it does, so that those pieces, as they're sweeping through that range of motion, are not catching on each other and grinding. So that's why we have to be really careful with the design, and they have to be a little bit wider typically. So these walls would be made a little bit thinner, and there would be more tolerance on the inside. Is how a real part would be made. But anyway, that gives you an idea how to set that up. If instead, I'm going to go to a 90-degree arrangement so that we have a reference. All right. If instead I wanted to adjust the angle reference between a complex assembly like this, which you very likely will have to do, you can expand the mate tree here and go back to find the specific one. In this case, I'm going to undo this one. And I'm going to set an angle, and I'll do it between this edge. So I'll do a new one. I'll do an angle reference between, actually, I'll do it between this face and this face. So that you can see how that's set up, because you might have to do a multi-component angle adjustment like this. So 30, 40. So it should be, one of these angles should be the same angle as the angle of the part. One of them is going to be an identity angle, all of those sorts of things. So if it had to be different, you could set it to be 90 degrees. Obviously, in a U-joint, that would be full bind, but it is physically able to go to a full 90-degree lock. It does have the cutouts for that. So you can drop it back down through the region. You can also individually drop them in terms of single degrees until it looks right. Takes you a long time to get there, but you can, because it takes a little while for SolidWorks to catch up. So that's not a method I would recommend, because that can burn time. You can overshoot. You can just lose what you're looking for. Because if you tried to lock it at 40 degrees, this is why you want to be really careful with constraints on assemblies. Now look what it tries to do. As you rotate through the range of reference, or through the range of motion here, it tries to always maintain that 40 degrees. And that's obviously way wrong. So if you then locked it in, so we'll get it back to something resembling, so I'm going to step out. That last angle reference we're going to undo, because you can always undo one, break one, and then put another one back and go, oh, that didn't work. That was terrible. You bring this face parallel. You could even do it with, this back face. That would be fine. Then you're back to being able to rotate this with the full range. All right. So that gives you a couple constraints on how to deal with a complex assembly, how to deal with tolerances, how to verify parts are correct, drawing multiple parts for an assembly, setting up dimensions, checking them, all of those sorts of things. So it's a lot of lesson, a lot of stuff, a lot of content. What questions do you guys have, those of you that are still standing? And we'll end the recording here for the sake of brevity for the rewatch.